And this is the screen you see if you open the software. And you see here different sections. This left part is for data reduction directly from camera images. And the right part is data reduction or editing for 1D scanned spectra. So here on the left side you have only 2D data. And we will start with raw files directly from my camera. Go to the desktop, in this case Beta Origa. And there are all my raw files. Hopefully there are. Yes, okay, here is 1, 2, 3, 4, 5 images with 8 minutes exposure time. You can mark it and open it together. What you're seeing is immediately scanned spectra because the software tried to find the scan line of the strip, and you see immediately from each single spectrum a graphic. I load the dark frames. It's also in the same folder. Where is desktop? So I have here 8 dark frames. I load the dark frames. If you want, you can check this box and then you see the dark frames in a 2D image. You can make it brighter so you see more the pixels, hot pixels. You can zoom in and zoom out and such things. Okay. But anyway, I want to have a master dark, and the master dark I will build with the save buttons. Now we have made the dark frame correction automatically, and it's always possible to switch it off and on. So maybe we can see some changes. Yes, if you look at graphics, you will see that the hot pixels are removed if I check this dark correction button. So what was in my opinion is that you always directly see what you are doing. Next I have flat fields. Sixteen flat fields in this case. Also the same, if you say save, then it build a master flat. Thank you. And you can also switch off and on the flat fields. Oh, hey. And you see the changing in the graphic. So at next I have made reference lamp images, and I do it always in this way that I start with a reference image, then with the spectra image, then the next reference image, spectra image, and I end with a reference image. That's necessary because of the temperature drift of the system. So you have, if you have more than one image and you want to overlay it, then I told you previously I had made it in 2D with programs like Registax or so, but this had a problem because you have no reference if it's always on the same level as the reference images. So in this case, you this program works always with all images and all references separately. It's always in the background. And if you make an alignment from the reference images, the system calculates over the timestamp of the images and correlate with the timestamp of the spectros and shift it pose in the same way with the same parameters. Reference images. Argon neon is in this case. You get a second graphic windows with the reference images. It's without mouse not so easy, but anyway. And also here you can make a dark correction. I made a previous made master dark. It's only a bias for me because it's a very short exposure, the reference image, and this camera has no really big dark current. Okay. Now we have in principle all files load I have made in this night. And what we can do, or what I will do at first, is to control if the scanning is okay from the system, the automatic scanning. So you can do it in this case that you check here manual. So I go back to zoom it in, and I can put it in the center, and you see here different stripes. So you have the red one is the middle line of the spectral stripe, the calculated, and the green one is the range where we can interpolate in Y. And I want also to control the angle of this scan and go to the far left and see it's pretty okay, and to the far right, and it's also okay for me. So in this case, I have nothing to do. You have also here the parameters. You see the pixel, the Y pixel is, the Y center is on 380 pixels dot 29, and the angle is 0.197 degree. And the span, this is this interpolation area, is in this case 6. And for me it looks good. So I say okay, this, or cancel in this case because it's the automatic. And I can do this for each of them. So looks also good. So if you, it's okay in this case, but if you're not satisfied, you can go with the slider and change this to change the angle, for example, or to change the span width, or to change the center of the scanning. So I will do it. Yeah, I will cancel it, and it's away. So okay, I'm satisfied with this scan, automatic scan. So I will switch. It's a little bit. Okay, so switch on all images again. And the next step is the background subtraction. background subtraction is an important thing because it's an additive error and make an influence on the highness of the lines. If you have, for example, you want to compare H alpha with H beta, it's another result if you do not subtract the background as if you do it, the ratio between these both. So that's an important thing. And also here I make a manual view. If it's okay for me, I have to go a little bit smaller. Okay. Normally you should be as close as possible on the spectrum stripe. In this case, the system said 19 pixels. I think it's for me too much. I will reduce it to 10. Then I try to go. You see here the result of the background. It's the average from upper and lower background stripe we have scanned here. I will go down to see if it's okay to use this. You have to attend that not the spectrum itself will influence the background image. So for that reason I would go a little bit away here. Okay. And standard, I do not subtract 1 by 1 pixel in this case because you get additional noise from the background in the spectrum if you subtract it 1 by 1. And for this case, also the standard is to make a polynomial over this result and subtract the polynomial. If you want to subtract pixel by pixel, you can check this box. For example, if you have distortion lines from the environment, so from lamps around of you, then you can make pixel by pixel. That makes sense. But normally, if you haven't some emission lines from the background, you should use the standard.
Question, Manfred.
Yeah.
Is it necessary to subtract darks and the background?
Yes.
Both?
Yeah, but in the dark, the background is not included.
What's the difference between background and dark?
The background is really the sky background. If you make a
What do you think it is?
so you have the slit, and the slit you have the small star. The small star make on the x-axis this small stripe, but above and below you have the sky scanned. Also you have the sky on the image, and the sky is not really dark, especially in our areas. And this is posed on the sky image. It's there, this information, and also in the spectrum is it additive, and you have to remove it from the spectrum. And that's the reason why we make sky subtraction, background subtraction. Okay, I'm satisfied with this, and in this case, if you have notation of your camera made or so, you can say, okay, I use it for all spectra, then it's not necessary to make each correction on each spectrum. Okay, so we have done now a dark correction, a flat correction. We have done a correction of the sky background. What we need is now an alignment, because I think that there is a temperature shift. So without mouse is a little bit hard. I think with the right mouse button you can zoom in. You see it's not well aligned. So okay, that's the alignment button here. Give you the chance to align. Then you get the question how you want to align. You can align over the spectrum itself. You can align over the reference lines, and you can align manually. Normally, if I have reference lines, I do the alignment with the reference lines. But sometimes, if you have made a mistake or so, it's possible that it's not so good working. Then I try it with the spectrum itself. So let us try with the reference lines. So he said that one of them is misaligned. But let us look. I think we have seen this. This is okay, I would think. The alignment is done. If you want to see it again, we can remove the alignment. Then you see the original state. We do it again. Yep. And the important thing behind is that not only the reference images are shifted now, also the spectrum itself is shifted, and with the same parameters as each single reference image. And this is the first step of the software. So you have reduced it to a 1D spectrum. Each of them is separated, stored, but you get also a stored summary. If you don't like this different highness because you have on the left side the ADUs of the camera, you can only for the display make a normalization. If you click here and say, for example, from here to here you want to normalize, then there is an overlay of this different spectra. But it's not in the data stored then. It's only for the view here. Good. You see here, for example, each name of each spectra, and the blue one is the sum of all. It's always live calculated. You can switch on and switch off the spectra in the graphic. So for example, if you want to see only the summary, then this is the summarized spectra. You can do it in one step if you make inversion here. You can exclude spectra if you see one of your spectra are not right exposed or whatever. You can give away this check and then it's excluded of the calculation, or you can remove it here. Okay, principle, that's the first step. If you press on calibrate, you get an information where the systems is storing the uncalibrated but 1D data.
One question.
Yeah.
Why is it so good to make the alignment from the spectra?
It's harder to get it automatically. So if you make it manually, it's equal. You take a line, for example, absorption line, and say, okay, I want to have this absorption line, and the next image, you click on the same absorption line, so then it's not a problem. But often, if you have very much lines, then the system sometimes could not fit all these different.
But if you have one emission line or a shell star, then I think it's not a problem.
I like to have more lines than one normally, because the system calculates the average then of all errors. So if you overlay it and you are not exactly, because it's very precise in the calculation, so you get 0.00x on left and then the next 0.05 on the right difference. It makes an average of all errors so that you get, for me, I think, the best result. Yeah?
In my opinion, the lines in the comparison spectra are narrow and they're strong, so it's better to use them.
Yes, that's right. Yeah.
Here you see the VHF line, for example, 2 peaks, and they're wider. Others are pretty small, pretty weak.
The reference spectrum, the lines are sharper.
Well,
Also, you have distortion often in the lines of the spectrum itself. So you have not a clear line shape. And that's also maybe more problem for alignment. So what you see now is the calibration area of this program. So in principle, we have three parts of the program. One is the transmission from 2D to 1D data. This was before. Now it's the calibration part. And at the end, it's the editing part, so the post-processing. You see here only the summarized spectra. But in the background, all spectra are in the background and will be calculated extra. So that's have this sense. You do not want always to have a summarized spectrum. Sometimes you make a time series, then you need each single spectrum. And I do not want to edit each single spectrum here. So the system works, you see only the summarized spectrum and you work here with it, but in the background, the system calculates for each spectrum extra. Yes, what you're seeing on the graphic, that it's still with ADU on the left side. And so in this case, it's not so nice because it's very low profile here. But you can check this only for the view to expand a little, yeah, to make an extension only, that you see it better. So, the first thing what you have to do is to have a reference list. It's a simple CSV list with the element, the wavelength, in this case in nanometer. And I have added some lists I need. So you can do it by with a normal editor or with Excel very easy by yourself. So I have added all elements. This is in principle the same what in the visual spec was included. And then I have made specially for my equipment argon neon for H alpha, what I need now. I import this, and you see here now the list. And if you have in the same name a JPEG included in the same directory, you show you also this JPEG, and this is a good help for you to find the lines. So, for example, here you can make an overlay and can see, okay, yes, the lines are matching very well here. It's easy to find it. What you have to do at first, you have to find the lines in your own reference spectrum. It's very easy. You can here define sensitivity. For example, I begin with 6. Say find lines. And you see the system found a lot of lines, and most of these are okay for me. So I will say, okay, that's fine. Then you have to define 2 of these lines, and all other can defined by the system itself if you click on one line. So these lines should be wide. Best thing is you have one on the left side, one on the right side, and not too narrow. So then it's easier for the system to find the lines then in the next step. So I will say, okay, this is my first line I have defined. I will click on it. Then it's selected. You see it on these red arrows here. And I select the wavelength which should be there. And you see that the first line is fill out. Then I take this one. And if you look at this is the 6666. And I define this one. And you have the second line now. And if we select the other lines, other known lines, so I'll make it a little bit upwards, then if you look in the list extend. I do not use the H alpha line. This is not very accurate here in this lamp. I use all other lines here. Which are defined in my JPEG here. So now you have the complete list filled out, and you get a result here, an error result here on the left side, but you have to attend this is in the moment linear. It's not a polynomial, and the grid is not linear, so you have to make a polynomial. It depends on the number of points you have. In this case, with 12 points, I would say the maximum should be 3, polynomial of 3 or 4. You can do this, and you will see immediately the change in the errors. Oh, this mouse is not always working. Yeah, 3. Okay. 4. You see it goes a little bit better, but I'm not satisfied with this error. What you can do now is to look where can be the problem. If you look on the left side, you see, okay, this is a really huge error here. If you click on it, you have the line selected, which is wrong. We can zoom in. Maybe I lock the y-axis so that we only zoom in x. Okay, the system calculated it in the barycenter. What you can try is to define by yourself with add or correct a line and click on the outside the wings, what the system also do, or you can define more narrow, for example, on this height, and it recalculates the barycenter, and you see, okay, the value is better now, but not 100% what I want. If you come not to a good solution, you can also say, okay, I clear the selected from the list, and you see the result is much better now in the sum of errors. We go back to one by one. Maybe we look for another bad guy. So yes, maybe this one, the last one.
I noticed something curious in the JPEG. There was one neon one line in the 6528 instead of 6532. I don't know if that is.
Just a moment. This.
JPEG.
I have closed the JPEG, so that's the problem. Just a moment. So if you search for these files, it's on the SpectroCalc 2 in the C drive, and then you have it here. No problem. Okay, it's okay.
I thought I saw the neon one.
Maybe in this resolution before it was not to read exactly. So anyway, okay. Yes. For example, we want also to clear this one. We get a better result now, and only for this workshop I would say it's okay for me. It's a really good result, and we can say we are satisfied and save the calibrated files. Now you get a question, do you want to make the result of the calibration 1 by 1, 2 by 1, or 4 by 1? You have to attend that we make now from a pixel model a new file to a wavelength model, and it's not linear. So if we say 1 by 1, then we lose a little bit because we have to interpolate always between the pixels and to the wavelengths, and you have a chance to get a better result if you take 2 or 4 to 1. Especially for radio velocity calculations, it can make a sense if you have a very good data material to make the linearizing or the transfer from pixel in wavelength in a higher resolution. Normally, the most cases I know, it's equal. So you can use 1 by 1 and you have only the same size as before after transferring in wavelength. Then you will be asked, want you to have only a summarized spectrum for the post-processing, or do you want to make a post-processing on each separate, on each single spectrum separately? So for time series, for example. In this case, I need only the summarized image. Each single spectrum is stored in a directory. But the post-processing now I will only make on the summarized image. So I have to look at the time. Yeah. Okay. So that's our spectrum with wavelengths now. The first thing we have to do is to correct the instrument curve. So you know your chip and all these things have a different behavior in the wavelength, and you have to correct this. The best way is to have a standard star in the near of the object, and you have in the same night make an image from them and make the instrument curve from the standard star and take it as a space for this. I do not have made this. For this reason you can also, it's not 100% the same, but you can also use the same star from other observers or a similar star with the same class. The problem is it's not my computer, and if you make a load reference, the libraries are not loaded, so I fear I will skip the Miles database because it's very... So it needs a little bit, it downloads now the libraries. Oh, it's fine. So now we have normally there's also the Miles database, and in the future I will make a link to the, I've forgotten the name of the database. It's a very open database. For me it was new.
Carlsberg database?
Oui?
Carlsberg? California?
Don't think so. But anyway, I have to look at home. I got in contact with them and they sent me a possibility that we can import directly from the software and the spectra, and so it will be nice. But it's work for the future for me.
Right. It's not possible to use our databases. Tickets or something like that is not possible to use.
Yeah, in principle you can use everything you have access. You can also copy or you can search in your own folders and take any spectrum. So it's only a fit. It has to be a fit file. So I know in LOD I have made only few spectra here, and the beta Auriga is not there, and I've seen in the LOD database there is no beta Auriga. For this case, I will now use a star of this low resolution. Yes, what we have is beta Auriga is A2, 4, I think. Okay, it's not really here, but I will take the A2, 5. So you should have really the same normally, but for this demonstration now, we'll take this one. What you see now is a new graphic window, this mouse. We have here 3 sections. One is your spectrum, one is the reference spectrum. And what we want to do is to find the continuum of both. In this case, we have a very broad H-alpha line, so that's not nice to find the continuum here. But what we can do is that we say we cut the fit from here to here, so that you go away from this, and you can also cut this line here, so that more or less you get a continuum shape, and you have to make the same on your spectrum. So we make also from here to here a cut, and it looks okay. And if you look now at the result here, you see the orange line is the instrument's response curve. The gray line was the original spectrum from you, and the pink line is the corrected. And this should be more or less on the same height as the reference spectrum, is the green one. So in this case, it's a little bit a problem because this was a so low resolution spectrum. That's not easy to compare. But normally, if you have in similar resolution, you get a better result. What you can do now is to say, okay, I use this instrument curve as it is, or you can say you make a polynomial with it. So one is more is linear, or 2, 3, 4, blah, 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 blah. Then this shape change in the way of polynomial calculation. So I let it as it is. And if you want, and you have always the same situations, or often the same situation, you can store all these steps you have done in a file, and next time you can get it back if you go to this list box. I do not this in the moment, so I say apply. And now you have corrected from the instrument's response corrected continuum. In some cases, you need a really leveled continuum for some measurings or whatever. Then you can make this with remove continuum. But these are different things you have to attend. So normally you should have the continuum as it is. Yes, what you can do is an ordinate scaling, so a normalization of the image, because you have still the ADUs here. If you are working on a project, then normally you know exactly the range where you have to normalize. I don't know it in the moment, so that I will make it with the mouse and say from here to here, for example. Then you see, okay, the ordinate is now 1 in this area. You can do it also with entering here the numbers, or with a preset. So if you have often this object and you want always have the same range, you can have here the areas where you want to normalize, and it's also possible to have multi-areas. Then it makes an average of these areas to normalize the y-axis. So if you want, you can also crop the image. So if you want always to have the same view, can compare some, you can calculate the signal to noise. Normally you have also an area defined in a project where you have to do that. In this case I will do it with the mouse. Looks not so bad. 400. And also here you can define presets for the next time. You can calculate the equivalent width. Also here you have normally the range given in a project. I don't know where it is here because on my computer I have it stored, but not here. So I will do it only that you see it also with the mouse. So you say from here to here, and then you get the calculation of the equivalent width. Yeah.
Because some lines can be fitted to the Gauss.
Yeah.
It's also a measurement of the equivalent feedback.
What's very important is to fulfill the header of the fits. So some informations are in your camera. It's filled out now. But you can get this information also from the SIMBAT. So if you enter here an object name and so say get from SIMBAT, then you get all this information from SIMBAT. Yes, here we see the type, A1. The date, the Julian date in the middle is calculated by the program itself from the images. The observation values from the observer there, you can enter here and you can make presets, but I have no presets now, sorry for that. And also the telescope informations you can set in the preset, resolution, spectrograph, and all these things. So you need not to change every time, because if you are always on the same place. So if you have done all these things, we say OK. So just a moment. Say OK again. Yes, normally you can do now this calculation of the heliocentric error. So that means all the movements of the rotation of the Earth, the rotation from the Earth through the orbit from the Earth through the Sun, the influence from the Moon is attended in this calculation of heliocentric correction. It's not possible in the moment because I have not filled out the place where I are, because it's not equal if you're in the equator or if you're in 45-degree. But you can calculate it, then you have here a number, and if you have calculated, you can also apply it. If you apply it, then this, in principle, the spectrum is the same, but the numbers will shift a little bit here on the x-axis. In the header itself, it's always marked if it's calculated only or if it's also in the data itself. So if another read your spectra and he sees exactly if it's only calculated or if it's also in the data attended. Yes, what you can further is to make telluric removal. For some reasons it can be necessary to make an shift of the, so an offset of the wavelength. You can make title, legend, text, what you want. So for example, if you press on title, you get from the header some information. You can shift it if you click on it and click on another place. You can make an automatic legend with the most important data from the header and what you have done. For example, normalizing the range, the signal to noise ratio. The range is also here included. You can add lines. You can also change the colors of it. So, for example, you want to make here a red line. Then we can make here a red line, for example. And if you want to have a blue line, the red line, you can also change it afterwards. Oops. Then you have, Then you have a blue line. And you can add a text. For example, red. And violet. Yes, and that is in principle. If you store this file, you get two files. One is the FITS data only, with the header and all the things. And one is the information about this text and lines and so. And if you open with my software next time again this object or this FITS file, then you get both together like you see here. So.
To remove the rubric, is this fully automatic or have
No.
you do something by hand?
So remove the lyric. It's not optimal in the moment, I think. You can choose between different Telluric models. You can load it. It's in principle a text file. Then you can change the strength and the wings and all this thing. And in principle, it's also possible to change parameters on lines, on different lines, separately, yes. But I'm not really happy with this in the moment. It's a work for the future to make it better, I think. Okay. Yes, if you have, for example, next time, so I will show you, if we save this now, we make a new, don't say result, and VEGA, so if we close this now, and next time we want to open it again, we press on this button. This is a open 1D spectra and projects for post-processing. We go to the result, open the FITS file, and you get also the information you have done before. It's possible that you also load other spectra in the same area. For example, we go back to the library here. When only for fun we take Gamma Cassiopeia here, and epsilon. And zoom in this area. We have the okay. Then you have an overlay from different, so for example, you have from another one the same object, then you can make an overlay and or from another time and can look at the difference. So in this case, it should not be restricted. And you've seen that the other spectrum had another wavelength area, so you get the complete information, but for your own spectrum, it's only this part because we have no more information. Okay, in principle, that was a quick view for the software. Questions? Yeah.
Spectrum goes from the highest to the lowest value.
Yes.
Do you intend to make a possibility to scale the wave?
I got this question before also. Yes, I should do that, but it's not in the moment. So in the moment, it's always the maximum you have in the data is the top end of the y axis. So the only thing you can do in the moment is that you stretch it. So for example, if you see that you can also change the ordinate here, and you see that's reduced on 800,000 ADU. This is a very much for me, and in our case we have only 60,000 or so, so it's very small. But if you check this box, you can stretch it. It's then we have only one because it's normalized. So yeah. Another question?
To safe spectra is with the ASCII file which I can produce, or only fixed files?
The spectrum itself?
Yes, if you finish and you make safe, what format is it?
It's normally a fit file. You can check this data, that is your DAT file, but there's no header and so inside. Yeah.
Just a little comment about the spectral type. I recall that it was A2, you found from but it was A1, so now I checked. So A1 was determined by Richard Gray.
Yeah.
And there was a later publication with high resolution spectra which actually established the binary orbit of beta Aurigae. And they have it as A2. But that's the difference between qualitative spectroscopy like spectral type, luminosity type, and digital one, temperature and log G.
Yeah.
So it's not a big deal.
I think we have seen a little bit in the movie before about such things.
Yeah, and for the telluric removal, I talked to quite a number of people. No one is satisfied with their routines. They're different, but it's hard to find kind of the perfect one.
Yeah. Okay. I think we are in time, so if no further question, we can close this nice round.